Mallik, you're
Thank you,
muted,
Arthur.
please.
I'm just opening up the slides. Can you see the screen?
Yes.
Awesome. So, great presentation by Babis and Arthur. So, I'm taking a slightly different look from 5G networks angle.
I'm really quickly, could you just place it in slideshow mode, please?
Yes. Is it properly visible?
Yes.
There we are. Good job. Thank you.
Thank you. So this morning you listened to Eric about how Ericsson's view in terms of 6G evolution. So let me just talk about what 5G and AI. As Babis said, although wireless is late to the AI party, but at the same time, wireless is transforming how AI is being envisioned. So when we look at how the technology evolved past, present, future, between the four layers, connectivity, compute, control theory due to AI machine learning, and in the content. In the 1990s, when the 2G was predominantly being deployed, it was all around the analog to digital when it comes to communication system side, and then circuit switching. But in the compute world, it's around mainframe. And in control theory, when Professor Raj Reddy was there at CMU, it's all about symbolic AI rule based. But the essence of this slide is that across these four swim lanes, the innovation took place in silos. But as we move towards 4G, we started seeing connectivity and compute integration due to virtualization, so-called NFV. And that integration extended into control theory, AI machine learning layer, as the world moves into 5G. And mainly it's driven by data-driven applications that Arthur talked about, where we not only provide massive connectivity due to 5G, but also you have edge compute to process that data at different locations in the network. And then you have AI machine learning to extract the value from the data. So you can see how these four swim lanes are coming together and converging. Convergence of 5G, edge compute, and AI to address that distributed infrastructure. Then, with respect to AI and 5G together, I think there are four main use cases. The first one is as the 5G provides massive connectivity across all the IoT devices, then how do you manage those devices? How do we extract the value from the data that's generated by those devices, so-called smart AI? And that extends into low latency and distributed AI. In other words, there are many mission critical applications where it requires AI to perform the training and inferencing closer to the devices at various edges of the network due to real-time nature. So that's where the 5G is transforming how AI is being implemented due to low latency mission critical applications. Last but not least, AI is also applied in terms of network optimization, network orchestration, just to optimize the 5G network itself, because the base station, for take an example, a base station, it generates petabytes of information in terms of the logs, alarms, and traps. When I was an engineer in 2G world, I used to sit in front of an element management system and look at all the logs and alarms, and then take a manual action on, okay, if I see loss of signal, then switch over to the next port or next line card. But now, with the petabytes of information coming in terms of alarms, traps, and logs, it's humanly impossible. So how do we leverage AI machine learning to really aggregate the data and analyze it and take action on it based on the alarms and logs, and then push the configuration changes down to the network, so-called closed-loop automation. So that's heavily used due to AI in the 5G network optimization. So this is just an example of how we are using AI across various network segments. You can see on the left side, you have various IoT devices connected to the network in the middle with the clouds on the right-hand side. So take an example of the 5G access. We are using AI to optimize antenna selection. We are also looking at optimizing MIMO in terms of sleep mode and other aspects of MIMO, and also predicting the sleeping cells for the energy efficiency reasons. So we are implementing multiple AI use cases for 5G access. We are extending that into 5G transport, mostly frontal backhaul scenarios. How do you optimize the transport resources? Then we are extending further into packet core to drive the much more dynamic policy-based traffic management. Then on top of that, we have Ericsson management orchestration, where we are implementing closed loop automation and service assurance, where we are able to collect the network operational data, analyze it, take decisions, and then push configuration changes down to the network, so-called closed loop automation. So we are implementing that using AI-based techniques. Then, apart from just network optimization aspects, we are also extending AI, so-called distributed AI. So when we look at a classic 5G distributed cloud deployment, we have the left-hand column, the deployment scenarios, so-called cloud to cloud, cloud to edge, edge to cloud, and edge to edge. On the right-hand side, you have got use cases, and the use cases can be bandwidth intensive or latency sensitive. Depending on whether it's bandwidth hungry or latency sensitive, you may be doing training and inferencing at different locations. So take an example of the last one, edge to edge. In the case of ultra reliable, low latency applications, such as mission critical smart manufacturing applications, we may be doing training and inferencing data closer to the edge or on-prem within smart factory complex itself. So you can see how we are extending an AI beyond the cloud into the edges, depending on the data model characteristics, as well as the use cases and business scenarios. And the last but not least, we are also taking AI into security. Security for AI, just as an example, and AI for security. In the case of security, when you secure the network on the most of the time we have rules, rule engine based, some kind of access control list, rule engines, and so on. But they're all static, predetermined. But in a dynamic world where the threat vectors are becoming extremely dynamic, and it's in a data-driven world, it's very important for us to apply AI to figure out what are the vulnerabilities. How do we do anomaly detection and response within few milliseconds? How do we have common visibility and monitoring across the entire infrastructure to figure out where the vulnerabilities are, where the anomalies are? At the same time, on the left side, securing AI, most of the data science engineers, they look at how do we develop data models, but they don't look at what are the vulnerabilities exist within the data, so-called data poisoning, so-called data confidentiality or integrity. So we are looking at AI for security as well as security for AI in such an environment.
Thank you, Mallik. We have to now move to the Professor Bhaskar. So